All right. Last meeting, we answered up to number 4. Okay, so today we'll just continue with our lecture. Now we're answering number 5. So the 2 vertical rods attached to the light rigid bar in the figure are identical except for length. Before the load W was attached, the bar was horizontal and the rods were stress-free. Determine the load in each rod if W equals 6,600 pounds. So basically, without this rod, this is its original form, right? There's no stress. Or rather, without this weight, there's no stress. Now, the situation is we added weight. Obviously, this will stretch because this weight will make this platform go downward. So the tendency of A and B is to stretch. And remember, whenever there's deformation, there's going to be stress. And that is what we're looking for. The load from each rod taken from its stress. Okay, let's begin. So we have this. That's right. W is equal to 6,600 pounds. Now remember, the first step is to use your equilibrium equations, or rather, the 2 steps here is to create your equilibrium equation or use your equilibrium equation and to create an equation out of the geometric properties or geometric deformation that happened. So first, let's find out our equilibrium equations. So for the past examples, we only use summation of forces vertical and horizontal, right? Because our forces are all parallel. Now this is a bit different. We're gonna use moment. So let's first try to get the free body diagram. Okay. So there's this rod is a reaction. So include that there. Okay, again, rods and cords, strings, whatever are all in tension. So assume tension here. So let's call that, this is now the force in this member. Okay, so let's call that PA. And then in the same way, this is rod PB. Again, that's what we're looking for. And then we have an applied load W here. Weight is always downward, and that is 6,600. Okay. All we need is an equation relating all of our unknowns. Okay. Now, the reason why we can't do summation of forces vertical or horizontal is because there's going to be a reaction here. Right? Let's call this AV, point A, and then AH. Okay? As you can see, if you do summation of forces vertical, we have 3 unknowns. So to get the least amount of unknowns possible, we'll use the equation for moment. So summation of moment, and then we'll take it above support to cancel your reactions. So about A equals 0. Then we just include 4, 2. Okay, let's begin. Let's start with PA, rotate about A, that's counterclockwise, so negative PA. Perpendicular distance is 4. PB, also counterclockwise, so negative PB. Perpendicular distance is 8. And then 6,600, that's clockwise, so plus 6,600. Perpendicular distance is 10 equals 0. Now let's simplify. You can use this equation as is, or we can simplify, divide everything by 4, right? And then transpose PA and PB to the other side to make them positive. You'll get, again, 4PA divided by 4, that becomes PA plus twice, right? A divided by 4 twice PB. And 6,600 divided by 4 is 16,500. Okay. Let's double check. 1650. Okay. And we'll call this your equation number 1. Okay. And then equation number 2 will come from relaxing your restraints and letting everything deform. So when we let everything deform again, this way it will make everything go downward. So let's have that. So this is the original span, right? And then its final location, because of this, this is a hinge. A hinge allows your bar to rotate. Okay, so this is going to rotate downward by a certain amount. So it's still fixed at this point. Then this will be the final position of your bar because of that. You'll see this is actually a total deformation of bar A, right? And then let me just include this is the total deformation of bar B, right? Okay. And then from this, we have similar triangles, right? We can use this middle one and then this larger one. So let's color that. Yellow for the larger right triangle. Yeah, and then blue. So that will make green. So similar triangles or biratio. From similar right triangles, we can use biratio and proportion. Okay. So side over side equals side over side. So sigma delta A rather, over base 4 equals this total thing, sigma B, delta B over total base, which is 8. Okay. Then we'll have multiply everything by 4 and then simplify. You'll get 8 delta A equals 4 delta B, and then simplifying 2 delta A equals delta B. Okay, and then from this, we can create your equations. Maybe so remember, we're looking for force. Okay, so we're gonna use the equation involving force for deformation, and that's PL over AE. So twice PL over AE of bar A equals PL over AE of bar B. Now you'll just sub in your values. So this is twice PA. Length of bar A is 4 feet. So make sure your units are uniform, everything in feet. So 4. And then AE. So they're homogeneous, right? They're identical except for length. So that means they have the same area and the same modulus of elasticity. So meaning this cancels out. Okay. Then equals PB times the original length of B is 6. Okay, let's simplify further. Divide everything by 2. We got 4 PA equals 3 PB. Now this is your equation number 2. Two equations, two unknowns. We can solve for PA and PB. Please solve what's PA first. Correct? Okay, not bad. 6,600 times 10, 16,500. So correct, Audrey and Mikhail, Manrique and Santos. So 4,500. Next, what's PB? Correct? Correct, Beatrice and Trinity. Pascual and Love. 6,000. And that is how you answer questions like that. Okay. Number 4. Any questions for number 4? Please answer in the chat. Number 5. Okay, no questions. Let's move on to number 6. The final question for indeterminate numbers. Okay. 3 rods, each of area 250 millimeters squared, jointly support a 7.5 kilonewton load, as shown in the figure. Assuming that there was no slack or stress in the rods before the load was applied, find the stress of each rod. And you have your properties of each rod. Okay, so basically you're looking for stress because of the 7.5 kilonewton. Okay, so straightforward. Okay, first step, you can draw your free body diagram to make things clearer. So you have your weight downward, always downward, 7.5 kilonewton. Then you have this. These are all strings or rods. And again, materials of that nature are always in tension. So let's call this force of your steel, or P of ST, whatever easier for you. And then again, the other 2 rods also in tension. This is PBR. PBR. Okay. Next, you have to have your angles. Now you can either figure out the angle or you can just use this. They're 25. And then from this you can do summation of forces vertical equals 0. Now remember, typically for the equations that we're used to, we need angle from the horizontal. But in case you don't want to do that, you can still use the angle from the vertical. Just remember, it's the opposite now. So the vertical component of PBR is PBR. Instead of sine, it's now cosine. Why? Because if you consider this right triangle, and then this is your angle, the vertical component is actually for cosine. Okay? So yun. So I'm just doing this to show you that you don't always have to get this angle if you don't want to. Okay? So PBR cosine 25 plus PST. We have another one upward. PBR cosine 25. And then we have this downward force. So negative 7.5 kilonewton. And then remember, we're given stresses. Standard unit for stress is Newton millimeter. So convert this to millimeter. Convert this to Newton. So times 10 raised to 3 or 7,500 equals 0. Okay. So now that you have that, actually I forgot to write our given. So let's just do that. Given area 250 millimeters squared. What else? EST and EBR. We already know for steel it's 200 GPa. And then for bronze, it was 83 GPa. Okay. So going back, we're looking for stress in each rod. So I'm gonna rewrite force in terms of stress. Remember, that's stress times area. So stress BR times area BR times cosine 25 twice, because there's two of them. Okay. Plus stress ST, area ST equals, I'm just gonna transpose that here, 7,500. And now that is your equation number 1. Okay. Now to get equation number 2, you're gonna remove the constraints and let your rods deform. So that means we're gonna remove this ring here. And it's gonna deform however it wants. Okay. So let's start here. And now what happens if you remove the constraint is, since this downward bar causes everything to stretch, okay, all of our bars will elongate, or all of our rods will elongate. So in the middle, the elongation of that rod is easy. It's just this way. So let's say this is its total elongation, right? So what about these two? Well, now they're just gonna elongate along its length. Okay, because again, we're removing the constraints. The same thing here. Okay. So that is how we draw our deformation with that kind of drawing. Let me just make it larger. Okay. So this is now your stress for steel. Okay. Deformation of steel. This is your deformation of bronze, and as well as this deformation of your bronze. And then the angles are the same. This is 25. This is also 25. And since it just elongated along its length, they're opposite vertical angles. So this is also 25 as well as this. Now, what is the relation of the deformation of bronze to your steel rod? Well, actually, hmm, this is how it deforms. Okay, so if you extend, eventually they create a right triangle with each other. Okay, so that's how your rods will deform if you remove this string. Now create an equation out of that. Okay, so relating deformation of steel to deformation of bronze, consider this right triangle. We have a right triangle, so we can use trig of functions, specifically cosine. So let's focus on this one. Cosine 25 degrees equals opposite, adjacent. The adjacent of this right triangle is stress BR, deformation BR over hypotenuse. And that's deformation or delta ST. Smooth things around. We have stress, deformation of bronze equals deformation of steel times cosine 25. Now we'll create equations for deformation. We're concerned with stress, so instead of PL over AE, we'll use sigma L over E of bronze equals sigma L over E of steel times cosine 25 degrees. Okay, so now this is stress BR. Next, we want to know length BR. Now, length, is it given? No. All we know is the length of your steel. Now, to get the length of your bronze, again, you'll have a right triangle. Okay, so let's use cosine. Cosine 25 equals adjacent. And adjacent of this right triangle is the length of your steel bar, which is 2.75 meters over hypotenuse. So length of bronze. Again, our standard unit is Newton millimeter, so I'll convert this meter into millimeters, so multiplied by 1,000,2750. Therefore, the final answer for your length BR is what? What's length BR? Correct, Sierra and Beatriz. Gutierrez and Pascual. Very good. Okay. It's 3034.29 and it's in millimeters. Okay, so now length of your bronze, we're gonna sub that here. So store, okay, subbing that here in LBR over E. E of bronze is 83 GPa. Convert to MPa, that's times 10 raised to 3. Then next, sigma ST times length is 2750 for steel, right? 2750 millimeters over 200 GPa, convert to MPa, then cosine 25. Okay, and now we have your second equation. Two equations, two unknowns. You can solve for what is being asked. Please solve what is stress in the bronze segment. Correct, Trinity and Aaron sa Mendoza. 6.30, I believe it's 32 if you didn't round off your values. And then unit and PA. Now please solve what's stress in your steel rod. Correct? Krishaline and Jade. Frias Lomibon. 18.54. And then unit MPA. That is our final answer. Any questions for number 6? Please answer in the chat. Okay, since you don't have any questions, that ends our topic for indeterminate numbers.